First time this time. It likes y'all. All right, example 3. So remember, we're kind of taking this in baby steps. We started with trying to determine the slope at the point 1, 2. So we did that, and we chose another point, and we got closer and closer. So we used values to help get there. But then we got clever, and instead of using another specific point, we defined the other point that we wanted to use h units away. And by doing that, we were able to come up with a formula for the average rate of change at that point. And then we could take the limit as h went to 0, and that gave us the instantaneous rate of change. So we cleverly circumvented having to have 2 points. But all that was good, and it was only good for at x equals 1. So now we want to kind of even make it more general. I'm going to, instead of using the point 1 f of 1, I'm just going to replace 1 with x f of x. And I'm going to treat this as if it were a constant. So as if it were a 1 and an f of 1. All throughout the problem, I'm going to treat it as a constant. And then I'm going to use the other point, x plus h, f of x plus h. So just like I did on the previous problem with 1 f of 1 and then 1 plus h, f of 1 plus h, I'm going to use those 2 points right there. All right, and then I'm going to set up, like we did in the warm-up here, the average rate of change between those two using my function. So let's come over here. There's f of x. We'll say that the average rate of change, we'll say it's going to be a function of h. I'll just call it a of h right away. I was calling it m yesterday, and then we called it a of h at the end. That's just the average rate of change as a function of h. So it's going to be f of x plus h minus f of x all over the change in the corresponding x values. Okay, there's that. That's just the difference quotient. If I simplify the numerator, or not the numerator, sorry, the denominator, the x's cancel and I'm left with h. And again, that's by design because remember, h is just a single variable representation of delta x, the change in x. All right, so right now this could be true for any function f of x. I haven't really applied it to a specific equation, but now we will. All right, so now we will evaluate it, and this is where my favorite problem from pre-cal comes from. We're going to evaluate it for the function 3x minus x squared. So in the numerator, to evaluate it, we're going to have 3 times the quantity minus the quantity squared. And that's how I'm teaching the pre-cal kids to do it. Right? 3 blob minus blob squared. Just replace the x with blob. And now we're going to plug into the blob our x plus h, our x plus h. That takes care of the first term in the numerator. And then we have minus, cuidado, cuidado, right? The function itself. So I'm going to put parentheses 3x minus x squared. All over h. And believe it or not, I harp on this in pre-cal over and over again. We work like 4 or 5 examples, and I talk about the importance of parentheses there. And then we test over it, and do you think anyone forgets the parentheses there? And thus forgets to distribute the negative? Yes, yes. More people than you would ever guess. It's sad. Okay? So we know that we either put parentheses there because there's 2 terms that follow, or we distribute the negative. But there's the setup for the average rate of change between an arbitrary point x f of x and another point that's h units away. So now if we just simplify this, we get 3x plus 3h minus square multiply double square and distribute the negative. We get minus 2xh minus h squared. This has a sledgehammer feel to it, doesn't it? And it should, because the only difference between sledgehammer and this is the sledgehammer already has the limit as h goes to 0 in front of it, and I'm choosing to do that at the end. Okay? We're still just finding the average rate of change. So if you expand it out, everything without an h in the bottom or h in the top should cancel. So here's your checkpoint to make sure that it does and that you've distributed correctly. So everything that's left, yeah, has an h. So we will factor the h out of those things. Make sure you keep the negatives where they're supposed to be. So h times 3 minus 2x minus h all over h. And then we can divide that out and we get 3 minus 2x minus h. This gives us the average rate of change then as a function of h, as a function of both x and h actually. Because I treated x as a constant, I can now let it be a variable again. So I'm going to calculate the average rate of change one time using this, just to show you how we could have used it. So let's come back up to the very top here. Let's do this one here, okay? So for this one, we found the average rate of change between 1 and 1.01. So in this case, our x was equal to 1, and our h was equal to 0.01, correct? We found the average rate of change between 1 and 1.01. So if I wanted to, I could just use those values for x and h, and I can come down here to my new handy-dandy little formula, and I can, I'll say this, when x equals 1 and it equals that, we get a of 0.1. I guess we could do it as a double variable, but I'll just do this. We get 3 minus 2 times 1 minus 0.01, and that becomes 1 minus 0.01, which becomes 0.99. So we get the same answer that we got above. But what makes this one even more useful is now, if I wanted to find the average rate of change between a number that wasn't 1 and something else, I can use it. Like if I wanted to know the average rate of change between 2 and 2.5, I can let x equal 2, and I can let h equal 0.5, and it's a much simpler calculation than having to set up the difference quotient, plug it in, and do all that tedious work that the calculator did for us, okay? So that right there is a pretty good little formula, because now it applies, unfortunately, just to this function here, but I can use it between any 2 points. But what are we after? We're not after the average rate of change. We're Newton. We're Leibniz. We want to find the slope of the, not secant line, but tangent line. I want to find the instantaneous rate of change. So if you remember then, h is the distance between the 2 points. Here's the magical step. If I simply take the limit as x goes to, or sorry, not x, my bad, as h goes to 0, where h is the distance between the 2 points of this expression here, 3 minus 2x minus h, we know how to evaluate that. I get what? 3 minus 2x. And again, I've been treating x as a constant this whole time. On the back end of this, I can let that be a variable. Okay? So now this is the holy grail. This is the distilled product that everyone wanted. This gives us now a formula that will find the instantaneous rate of change at any value of x on that parabola. We circumvented needing 2 points. We call this function, because it's related to f, it gives us the slopes, we call it f prime of x. That's what we refer to it as. We call it f prime of x. And that's going to become known as the derivative function of f. Okay, we use kind of the same notation. If the function's name was g, we'd call that g prime. It just shows that it's related to f. So f gives us our y values, right? F of x still gives us our y values, but now we have this other function f prime that gives us our slope values at any single point, just by knowing the x value. So let's try that out. Let me copy this and come up here, because we discovered that by the method of exhaustion, right? Way back up here when we did it numerically. We saw the writing on the wall, right? We saw that our average rates of change were increasing, 0.5, 0.9, 0.99, 0.99, limited by the value of 1. So we said that. We said that we conjectured that the slope of the tangent line of our parabola at x equals 1 was 1. We conjectured that that slope was 1. Well, now guess what? We do not need to conjecture anymore. Because we have this function, let me go ahead and rearrange it a little bit, because we like the function on the left. We'll call that f prime of x equals that. If you want to know what the slope is at x equals 1, just evaluate this new function called the derivative, f prime of x, evaluated at 1, and you get 3 minus 2 times 1, which of course is 1. We get the slope at that point by direct substitution, essentially. That's fantastic. That's amazing. So how can we go about getting that function every time for any function? Well, if we take the limit at the end, that's going to be fine. But we can also insert that limit in front all the way up here. If I insert that limit in front right there all the way at the top, I can then use that setup for any function f of x, okay? And that's what we have right here. We're going to go back and verify a few more points. So this is hugely important. This is a great breakthrough. This is a limit definition of the derivative function. Here it is. Let's say we have some differentiable. What does that mean? A function is differentiable if its derivative exists. We'll just settle for that now. Its derivative function, which we're calling f prime of x, is defined by this. If the limit as h goes to 0, we'll throw it in the beginning of your difference quotient, f of x plus h minus f of x, all over, and remember this is just x plus h minus x. It's delta x or h. If I had just thrown that at you, that would have been kind of like disgusting, right? But I didn't. We got there by evolving towards it. So not only do you now have that memorized, hopefully, but you have an appreciation for it, you know exactly what it means. Okay? That will give us that holy grail magical equation that will allow us to just drop in any value of x and find the slope or the instantaneous rate of change at that point. All right, so that was one of the motivations of calculus, how to find instantaneous rate of change. But you know what was another impetus for finding calculus? Max-min problems, okay? Max-min problems. For parabolas, it wasn't really a big deal. We happen to have a parabola. But if you could model something by a parabola like this, like profits in dollars against units sold or something like that, wouldn't you want to maximize your profits? I bet you would. We would need to know then where, that is, for what value of x, we need to produce that to maximize our profits, okay? For a parabola, there's a formula for finding the vertex, but for other types of functions, other polynomial functions that look like that, there is no formula. But we can use now the power of calculus, the power of the derivative, to help us find it. Because if the derivative gives us the slope of tangent lines at any point, what do we know about the slope of the tangent lines at these local maximums and minimums? Good. They're horizontal lines, and so their slope is 0, and therefore their derivative value is 0. The tangent line is horizontal. The slope of a horizontal line is 0. If the derivative gives us that slope at any x value, their derivative value is 0. That's a powerful tool now to find those x values. Let's do it here. We know it's a foregone conclusion, right? We know that for a parabola, it's just the average of the x-intercepts. There's also negative b over 2a. You can complete the square and put it in vertex form. Lots of ways. But let's verify it. If I take my f prime of x and I set it equal to 0, that's the same as saying 3 minus 2x equals 0. I get negative 2x equals negative 3, and x then equals 3 halves, which is 1.5. It works. That's amazing. It works. So this new calculus, as you can imagine, was a hot commodity back in the 17th century. It spread like wildfire. And that's when Newton then caught a hold of Leibniz's work, who was getting all the credit, and said, hey, wait. I discovered it first. I just didn't publish mine, right? So, okay. And it turns out that, again, they did discover it independently. Who actually discovered first is unknown, but Leibniz published first, and Newton ended up getting all the credit. So there you go. We have the derivative now. We have the derivative. We have a way to find a function that allows us to find the instantaneous rate of change at that value of x. That's what Galileo was ever able to find. Poor Galileo. He did not succeed in getting this equation. Okay, but we have it now. And if you listen carefully, you can hear Galileo in his grave. What is he saying? I don't know. You lucky kids, grr, you take it for granted. Why haven't y'all fixed the Leaning Tower yet? Right? I don't know. Anyway, he would think, maybe after all this time, he would think with our advances in, architecture and structural engineering that we would have fixed the Leaning Tower by now, but we didn't, right? Okay, so there are other notations that we use for f prime. We will use y prime, like if you have an equation that's y equals instead of f equals, we'll use y prime. But we also use this one, and this is kind of my personal favorite. dy over dx. You can read it as dy over dx. You can also read it as this. dy is called the differential of y. We'll talk about differentials later in the year. Differential of y, and of course dx would be the differential of x. There's a couple of reasons why I like this notation. First of all, it preserves the operation that we were doing, right? Which is division. When we found the average rate of change, remember the average rate of change from Algebra 1 was delta y over delta x, yes? Delta y over delta x. Delta y is a measurable change in y. Delta x is a measurable change in x. So dy over dx preserves that slopey feeling, doesn't it? dy over dx feels slopey. So what's the difference between the differential of y and delta y? Well, delta y is a measurable change in y, whereas the differential of y is so infinitesimally small, it's not measurable. And the same thing for delta x. It's a measurable width, whereas dx, the differential of x, is infinitesimally small. You cannot measure it. Who called their calculus the method of infinitesimals? Leibniz. That's the other reason I like this one here. And this is Leibniz getting the last laugh. Newton kind of gets the credit for calculus. Most people have heard of Newton. But the joke's on Isaac Newton. We still use Leibniz notation to this day. And we don't use Newton's notation. Newton's notation was archaic, and you'll see later, Newton actually divided by zero in his calculus, which he and Chuck Norris are the only people I know to have ever pulled that off. People knew he divided by zero, but because he was Isaac Newton and the calculus worked, they turned a blind eye to it. They're like, I don't know how he did it, but it works. Just use it. Okay. So we'll look at that later on, how he divided by zero. But Leibniz notation we use, okay, has that slopey feel, and we're kind of standing up for the, the little guy. Okay. What time do we go to lunch? 17? We got time for this. All right, so let's try it out with a fresh function. Let's get rid of that parabola, right? Given the graph of the square root of x minus 2, first of all, what does that look like? It's your parent function, radical x, and the x minus 2 moves it to the right 2. So it looks like this. It comes up vertically and goes like that. So it's half of a parabola turned sideways. All right, I would love to be able to find the slope of that graph at its instantaneous rate of change at any point. First of all, what do you think the slope is at 2? If you were to draw the tangent line there, what would it look like? Right, it would be vertical. You'd have a vertical tangent line. Just like the parabola would have a horizontal tangent line there. This has a vertical tangent line at x equals 2, and so the slope doesn't exist, right? The slope doesn't exist. And therefore, the derivative, we're calling this one f, the derivative at 2 should also not exist. It should be it should be infinity, right? The slopes are positive as you go to the right. So here's kind of an interesting thing already, before we even get into the equation. The function is defined at 2, but because its slope is infinite there, the derivative is not defined at 2. So the derivative function that we're going to find has a smaller domain than the original function, okay? And sometimes that happens. It's never going to be bigger. It's either going to be the same or smaller. Now, I wonder if the derivative function that we're about to find knows that it's not supposed to generate a value when I plug in a 2. Because when I plug in a 2 here, 2 minus 2 is 0, the square root of 0 is 0. But I wonder if the derivative function knows that when I plug in a 2, I'm supposed to get infinity. I wonder if it knows. All right, let's see if it knows. Let's set it up. It says, it says to describe what the y values are doing and how they're doing it. Our y values are doing what? Increasing how? At a what rate? At a decreasing rate. Yeah, they're increasing at a decreasing rate. Later on, we're going to call that concave down like a frown. Okay? So let's go ahead and find the derivative. So let's set it up. This will help you remember it every time. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. There's your setup. If you do that every single time, you'll reinforce that. Okay? Now we'll set it up specifically for our function, working straight down with an equal sign. The function evaluated x plus h is the square root of x plus h minus 2 minus the function itself. We don't need parentheses because the radical protects it, all over h. All right, there's the setup. I just replaced x with x plus h in the first one, and then the function itself here. There's the setup. Everyone okay with that? All right, so now we fall back into 1.4 land. Now it's just a matter of evaluating the limit, which never not first, direct substitution, you do get 0 over 0. And you know what 0 over 0 means? It means you probably set it up correctly. If we let h equal 0, we're back to 1 point. That doesn't work. So how do we evaluate this? We have a method, retcon, okay? So that's the square root of x plus h minus 2 plus the square root of x minus 2. Was this on the worksheet? I don't know. Maybe it was. But because we've practiced evaluating limits now, that is not going to be the obstacle to getting the correct answer. Or at least that was my intention. All right, in the bottom, I'm just going to leave it as h times all of this, x plus h minus 2 plus square root of x minus 2. And in the top is where the action's at. Radical times radical is radicand. And now we got to be careful here. The inside and outside cancel, but we have minus then the quantity x minus 2. I'm going to go ahead and distribute it. Are you okay with that? We're running out low on time. Just make sure that when you have that quantity there, you distribute. So that's going to be a minus x and a plus 2 when I distribute to the quantity under the radical. All right, so everything should work out now that doesn't have an h in the top should cancel, leaving just a sole h in the top, which then can do what with the h in the bottom? Divide out, leaving a 1. So we did a couple things in that line, right? We canceled first, then divided out. And now any h that's left, by the way, that's the average rate of change formula. But now we can plug in a 0 to any h that's left, and we get 1 over the square root of x plus 2 plus the square root of x plus 2 is 2 square root of x minus 2, x minus 2. And there it is. You hear Galileo? That's it. We now have the derivative function. What do we get when we plug in a 2 into the derivative function? We get 1 over 0, which means it's what? D and E, it's some type of infinity, and it's positive infinity. OMG, as y'all say? Well, y'all probably don't say that anymore. It's probably something new. The derivative function knows that even though the function's defined there, the derivative is not. It gives you an infinite slope at 0. Wow. Wow, that's insane. What about over here at 11? What's the slope right there at 11? How fast is that graph changing at 11? Oh, it looks like it's going to be some small number, right? I wonder what it is. Let's plug it in. What would be f prime of 11? It's 1 over 2 square root of 11 minus 2, 9. Good choice on my part. Square root of 9 is 3. 3 times 2 is a 6. Is that reasonable? 1/6? It's pretty flat there, right? It's going up 1 over 6, up 1 over 6, or up a 6 over 1, up a 6 over 1. That's fantastic. That's amazing. It knows that the slope is infinite at 2, where the function is defined, and then it knows the slope everywhere else. What do you get? What do you get if you try to plug in a value to the left of 2 that's not even in the domain of the function, like 0? What do you get? You get a negative under the radical. It knows that too. Wow, that's pretty cool. Wow. So, wow. I think we'll stop right there for lunch with the wow factor intact. Pretty impressive.